Bismillahirrahmanirrahim. Dear students, I'll start lecture number 2 of week 13, and in today's lecture we'll discuss three important concepts. First will be the probability models for derived random variable. This will be my first topic. The second topic we'll discuss transforming continuous random variables, how we can transform one continuous random variable to another continuous random variable. That is a very interesting topic. And the third and the last topic of this lecture and this chapter is conditioning a continuous random variable. So I'll start topic number 1, and that is about probability models of derived random variables. You know, if we have a random variable y that is a derived random variable derived by applying some functional form g on the random variable x, what is the PDF of y is basically the concept of this topic. So, you know, in the discrete case, in chapter number 2 and 3, we used to find the PMF first, and from there you could find the CDF. But here in continuous random variables, I told you the process is in the reverse direction. So in continuous case, we always follow a two-step procedure, so that two-step procedure is as follows. First, in the first step, you find the CDF of the derived random variable, which means f sub y of y here, and you know this is nothing but the probability that the random variable y is no greater than this, the total probability. And in the second step, we find the PDF of the derived random variable, and you know this is obtained by differentiating the CDF with respect to y. So we will follow this two-step procedure to find the PDF of the derived random variable y. Remember, y is obtained by applying some functional form g on the parent random variable or the source random variable x. So how we can do that, I'll straight away go to an example and explain how we can do that. So we have now an example, a simple example. And that says a resistor R has a value uniformly distributed between 900 ohms and 1100 ohms. What is the PDF of the conductance Conductance is obtained by applying some functional form on the resistant, and you know this functional form is simply 1 over R. So we need to find the PDF of the function of the derived random variable 1 over R. So our parent random variable, the source random variable is R. Its distribution is given and that is a uniform distribution between 900 and 1100 ohms, and we need to find the PDF of the conductance which is another random variable, call it 1 over r for a while. So now we try to solve this. As I said, we'll utilize this two-step procedure. First, we'll write the CDF of the derived random variable, and once we have found the CDF of the derived random variable, we'll simply differentiate that to find the PDF, the probability distribution of the derived random variable. So now we know that we are given that the PDF of the source random variable R is simply 1 over 200 for R greater than or equal to 900 and less than or equal to 1100 ohms, and it is equal to 0 otherwise. Why? Because this is the range from 900 to 1100. So 1 over 1100 minus 900 ohms is 1 over 200. So this is the uniform probability distribution PDF of the parent random variable R. Now we are asked to find the PDF of, say, the derived random variable Y, which is given as 1 over R. So I say my derived random variable is Y, and its functional relation with R is simply given as such. So now we apply this two-step procedure. So first we find the CDF of R. So in step 1, we find the CDF of R. And you know it is 0. If you recall the formula, the expression for the CDF of a continuous uniform random variable, you will be easily able to understand why I wrote this expression that I'm about to write. So it is 0 for R less than or equal to 900. It is R minus 900 over 200 for R greater than 900 and less than or equal to 1100, and obviously it is 1 because it is a CDF for R greater than 1100. So this is the CDF of the parent random variable. Now we'll find the CDF of the derived random variable. Remember this. So the CDF of the derived random variable is f sub y of y, and this is nothing but by definition the probability that y is less than or equal to some number y. And if you now replace the functional relation between r and y, we can write this as the probability that r is greater than or equal to 1 over y. Remember, we have replaced y with 1 over r, and when we write it as r, so the inequality reverses. And I can easily write it as 1 minus the probability that r is less than or equal to 1 over y, and so I can write it as 1 minus f sub r at 1 over y. So you see, this is nothing but the CDF of r till the point 1 over y. So I can write it as such. So now if I utilize this equation here in this particular equation, I can simply write this as 1 for 1 over y less than 900. Simply replace r with 1 over y. and I can write it as the second part is 1 minus 1 over y minus 900 over 200 for y between, sorry, 1 over y between 900 and 1100, and it is equal to 0 for 1 over y greater than 1100. So now we have been able to write the CDF of the derived random variable y. Okay, and the relation between y and r is simply like this. So y is nothing but the conductance here. So if this is the case, we can now move on to step number 2 and differentiate the CDF of the derived random variable to obtain the PDF of the same derived random variable. So our PDF of the derived random variable is simply d f sub y of y over dy. So if you differentiate this particular expression here, if you differentiate this particular expression one by one, the derivative here is 0, the derivative here is 0, the only meaningful derivative will be for this particular range, this expression and this range. So the derivative ultimately becomes 1 over 200 y square within a meaningful range. So you see how we can be we are able to easily find the probability distribution of the derived random variable y from the parent random variable or from the distribution of the parent random variable r by applying the two-step procedure. First we find the CDF of the derived random variable, and then we differentiate that CDF to obtain the PDF or the probability distribution of the derived random variable. So this was our first topic. A few related theorems, just two theorems, and then we'll complete our topic. And those theorems are simple to follow. There is a theorem that says that if we have a random variable y which is obtained from the parent random variable x by transforming it as such. So you simply scale the parent random variable. So if you have this relation and a is greater than 0, then the PDF of y is simply 1 over a times the PDF of x, but replacing x with y over a. And secondly, the CDF of this derived random variable obtained by scaling the parent random variable, given that a is greater than 0, is simply the CDF of x at y over a. So you replace in the expression of the CDF of x, you replace x with y over a, and you obtain the CDF of y. And to obtain the PDF of the derived random variable y, you simply find the PDF of x, replace x with y over a, and scale it with 1 over a. You can prove that. It should not be that difficult. Let me prove this. So as a proof, you know, f sub y of y can be written as the probability that y is less than or equal to some number. This is by definition. So if we do this, we can write it as probability that y, which is nothing but ax, is less than or equal to y, and so we can write it as the probability that x is less than or equal to y over a. So now you see this is a CDF of x. By definition, the probability that x is below or equal to this number, so we can write it as f sub x at y over a. So this is basically the proof of this particular expression. And now if you simply want to find f sub y of y, you differentiate the CDF of y with respect to y. So if you differentiate that, uh, you will have 1 over a times f sub x at y over a. So you see this is an elegant theorem. This theorem states that multiplying a random variable by a positive positive constant stretches the original PDF if a is greater than 1, or shrinks the original PDF if a, the constant, is less than 1. So this is the relation between the PDF and CDF of a derived random variable, given that it is derived by scaling the parent random variable. But what about the shifting effect? So there is another theorem that takes care of this shifting of a parent random variable. So now suppose you have a derived random variable v, which is obtained by simply shifting the parent random variable by b. So if this is the case, then the PDF of the derived random variable will be simply obtained by the PDF of the parent random variable by replacing x with v minus b. And the CDF of the parent random variable can also be obtained by the CDF of the PDF of the derived random variable v can be obtained from the CDF of the parent random variable by replacing x with v minus b. I'll leave the proof of these two expressions as homework. So do prove these two relation. It is so simple. As I said, you first find the CDF of the derived random variable, and you know you can find it using something similar to this. So if you remember these steps and understand these steps, you should be able to find this f sub v of v, and once you have obtained that, you simply differentiate to find the PDF of the derived random variable. So if you can do that, you must arrive at these two expressions. So students, this completes our first part of the lecture, and that was about probability models of derived random variables. I'll move on to discuss another uh, important and interesting topic, and that is transformation of the continuous random variables. So my next topic is transforming the random variables. In this chapter, we'll discuss only continuous case, which means you have a parent random variable or a source random variable x, and you apply some functional form g on the source random variable x, and you obtain a derived random variable y. So how can you do this if you have the expressions available for x and y and the functional form? So we let that our derived random variable y is obtained from the parent random variable x or the source random variable x. So this is now your source random variable, and this is your target random variable. Call it target, call it derived random variable. It is up to you. But the probability, as per the definition of the PDF, you know that the probability that the random variable x is greater than or equal to this value and less than equal to x plus dx, just a little more than x, and this is nothing but called the PDF of a random variable x. But you know, if this relation is given, then this probability must equal to the probability that the y also lies in the range y and y plus dy. So if that is the case, uh, let me write so that you get some complete understanding. But this probability must equal the probability that the random variable y lies in the range y and y plus dy. This should be automatic. So if this is understood, we can simply write that the PDF of y times dy is equal to uh, the PDF of x times dx. This is positive if the function g is monotonically increasing, and this is equal to minus times f sub x of x dx if g is monotonically decreasing. So basically f sub y dy is equal to plus minus f sub x dx. So in totality we can write it as f sub y of y is equal to or the absolute of f sub y uh, times dy is equal to absolute of f sub x of x dx. So we can simply write it now as f sub y of y is equal to f sub x of x times dx over dy absolute. So remember, we will use this relation to transform x into y if we know the functional relation between x and y. So we'll utilize this formula. All this basics, or basically given are presented to arrive at this particular formula. So from here onwards, to find the PDF of a derived random variable, we'll utilize the PDF of the parent random variable or the source random variable, multiply it with the dx by dy, and we'll find this target distribution. So let me do an interesting example about that. You will hopefully understand uh, all the points then. So I solve an example. Sorry. So we assume that we have some PDF of the source random variable x, and it is given as e raised to power say minus x square for x greater than or equal to 0, and we let y as g of x, and that is now x square. So this is the PDF of the parent random variable of the source random variable, and the relationing functional relation between y and x is given as y is equal to x square. So our goal is to find the probability distribution of this derived random variable. So I try to solve it. Remember, my target is to utilize this particular formula, that is the PDF of the derived random variable is equal to the PDF of the parent random variables times dx by dy. So now you know that if y is equal to x square, then we can write x is equal to plus minus under root y, and this then implies that dx over dy is simply plus minus 1 over 2 times under root y, and therefore we can write the PDF of the derived random variable as what? The PDF of the original random variable, the parent random variable, the source random variable time dx over dy. We have already found dx over dy. We already have the PDF of the source random variable. So now we can write it as e raised to power minus x square, which is the PDF of the source random variable, and dx over dy was obtained here. So it is 1 over 2 under root y. But we have to write it in terms of y. So what is y? Y is nothing but x square. So we can write this expression as 1 over 2 times under root y into e raised to power minus x square. But x square is y, so we can simply write it as e raised to power minus y, obviously for y greater than or equal to 0. So we have been able to very easily and simply transform a random variable x into y through this relation, functional relation, and this basic formula. So remember, this formula is very important to transform a continuous random variable into another continuous random variable, and we can then find the probability distributions of probability distribution of the derived random variable. I'll move on and solve one more example. That example is a little complicated but not difficult. If you understand this example, you will be able to grip the concept of transformation of the continuous random variables. So next example, example 2. And first, let me write the statement of the example because I have taken it from a few other sources. So we assume the sinusoidal signal x, which is given as cos omega t. T is simply time, omega is the frequency, where the signal has random frequency omega that varies uniformly in the range omega greater than or equal to omega 1 and less than or equal to omega 2. So you see the relation here. Omega is your source random variable and x is your derived random variable or the target random variable, and when you apply a functional form cosine on the parent random variable or the source random variable omega, whose distribution is already indicated here, and that distribution is uniform continuous distribution between omega 1 and omega 2. So the distribution of the source random variable is already indicated. You are asked to find the distribution of the derived random variable or the target random variable x. So we will while solving this example find the distribution of the target random variable, sorry, the parent random variable, and the 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 question asks that the question says that the frequency omega uh, the frequency is represented by the random variable omega. So you see this omega and this omega are basically the same thing. This is the random variable and this small omega is some occurrence of that random variable. So we'll we will write the distribution of this. This is the random variable and this is one of the occurrences of that random variable. The question says that we need to find the expectation and of omega and expectation of x. So now what is the problem to be solved? We know we have a relation between the parent random variable x, the source random variable, sorry, the source random variable omega, the parent random variable omega, and the target or the derived random variable x. The distribution of the source or the parent random variable is given, and that is that it varies uniformly, or it is uniformly distributed in this particular range. It is the frequency, so the random variable as a capital omega is written as such, and now we are asked to find the expectation of the source random variable and then the expectation of the target or the derived random variable. So we now approach this particular problem. So we start the solution part of this problem. Since omega is uniformly distributed, so we can write f sub omega of omega as simply 1 over omega 2 minus omega 1. There should be no confusion about this. So if this is known, then the expected value of the random variable omega is simply integral from omega 1 to omega 2 omega times f sub omega of omega d omega. This should be easy. This is simply the formula of the expectation. And so we can write it as 1 over omega 2 minus omega 1 times integral omega 1 to omega 2 omega times d omega. So you should be able to know the relation between this expression and this expression. F sub omega of omega is nothing but this, and since these are two constants, so these have been taken out of the integral sign, and the rest is simply omega times d omega. So you simply integrate that. So if you integrate it, you will get it over 1 over omega 2 minus omega 1 times omega square by 2 from omega 1 to omega 2. So if you do a little bit of substitution of the values here, we can reach here. The expected value of omega is equal to 1 over omega 2 minus omega 1 times 1 over 2 times 1 over omega 2 minus omega 1 here times 1 over 2 here times you simply substitute omega 2 and omega 1 here for omega. So you get omega 2 square minus omega 1 square. And so this is 1 over omega 2 minus omega 1 times 1 by 2 times omega 2 minus omega 1 into omega 2 plus omega 1. So this crosses with this and you get omega 2 plus omega 1 over 2, which means exactly the middle value, and that should be obvious. Why? Because it is a uniform continuous distribution. So now we have been able to find the first required expectation, the expectation of the parent random variable omega. From here we will try to find the expected value of the derived random variable x. But remember the relationing between the two. The parent random variable and the derived random variable are related as such. You find the distribution of the parent random variable and then apply this dx by dy, multiply it with this distribution, you get the distribution of the derived random variable. So we'll use the same procedure here, and for that we first need to know the expectation the distribution of x. Remember, x is now your derived random variable. Here in the basic relation, x was your parent random variable and y was your derived random variable. But in this example, x is your derived random variable and omega is your parent random variable. So please do not confuse these. So now I move and write. Now you know f sub x of x is, which is your derived random variable, is related to the parent random variable through this relation, and you know x absolute is less than or equal to 1 because of this functional relation. It can not go beyond -1 or +1 because it is cosine. So say this is my equation number 1. Now we already know this. Okay, how? Because we know that it is uniformly distributed between omega 2 and between omega 1 and omega 2. So we simply need to find this part of this equation, and then we plug it in and we'll find the distribution of the derived random variable x. So to find this, first please note that as x is equal to cos omega t, so omega is equal to 1 over t times cos inverse of x. Okay, and this is simple. So please, as a homework, you need to arrive from here till here. So use trigonometric formulas to reach at this from here till here. This should not be difficult for you. Yes, sir. So now we know that if x is equal to this, then omega is equal to this. Now simply differentiate omega. So if we differentiate omega, we obtain d omega, obviously with respect to x, as 1 over t times under root 1 minus x square. Again, you simply take this as homework and use the differentiation formulas to arrive from here to here. So assuming that we have been able to correctly find the derivative, equation number 1 now can be completed. You can plug in the values of d omega over dx, which is this value, and you already know the distribution of omega, which is this. So if you multiply this with this, you'll get the distribution of the derived random variable x. So now equation 1 becomes f sub x of x, and that is equal to 1 over omega 2 minus omega 1, which is f sub omega, times d omega over dx, which is 1 over t times under root 1 minus x square. Say this is my equation number 2. So now from equation 2, we can find expectation of x. It is simple. You know the distribution of x now, so you can easily find the expectation of x. And that is as such. Expectation of x is equal to integral -1 to 1 x times f sub x of x dx. And so this can be written as 1 over omega 2 minus omega 1 times 1 over t these two are taken out of the integral, times integral minus 1 to 1 x times 1 over 1 minus x square under the root dx. So now this should not be difficult from you from here to move to your final expression for the expectation of the derived random variable x. I'll not give you the answer, but this is simple. If you perform this integration and obviously multiply with these, you will reach a certain value. What is that value? I'll keep that value for your homework. So you simply find this integration, use the integral formulas, and arrive at the final number or the expression. I'll not tell you, but maybe in the interactive session, Xavier will tell you what was the final result here. So you see now we have been able to find the expectation of the derived random variable by using a certain procedure. So this is now simple. I hope you have understood almost all parts of today's lecture. And the third part is now the conditioning of a continuous random variable. So I'll move on to the next topic, and that is conditioning a continuous random variable. This is easy. If you know the concepts of conditioning a discrete random variable, then this should not be a big deal. So conditioning a continuous random variable basically means the distribution of x given some event b has occurred, and that should be equal to the original PDF of x, which is f sub x of x, divided by the probability of the conditioning event, which is given as such, and obviously for all x inside B and it's equal to 0 otherwise. This is effectively the same formula that we have already discussed and understood in chapter number 2 and 3 about conditioning a PMF. So now we are simply conditioning a continuous random variable, so we'll utilize the PDF. What about the expected value of x given b? This is again very simple. Integral on all the range x times the PDF, but which PDF? The conditional PDF. So it will be f sub x given b of x times dx. And what about the variance of x given b? That is nothing but the expectation of x minus the mean. But which mean? This mean. So this can be written as mu sub x given b, and then you simply square it. So this ultimately reaches at expectation of x square given b minus expectation of x given b whole square. So this is the formula for the variance, conditional variance. This is the formula for the conditional mean, and this is the formula for the conditional distribution. I'll solve one example to convey the concept of all these things, and this is an interesting example. Please follow that carefully. The last example of today's lecture. Suppose t in minutes is the call duration in a phone exchange with expected value of 3 minutes. And suppose that distribution of the call duration time is given as 1 by 3 e raised to power minus t by 3. So you see this is an exponential distribution where a is 1 over 3 and t is obviously greater than or equal to 0 and it is equal to 0 otherwise. Now what about the conditioning applied over here? So I now put the conditioning here. So I say for calls that last at least 2 minutes, what is the conditional PDF of T? So please understand the nature of the question. This is the distribution. This is the unconditional probability distribution of call time or call duration if the average call duration for that phone exchange is 3 minutes. So it includes any call of 0 duration onwards. But now I put the conditioning event and I say for all the calls that last at least 2 minutes, what is the conditional PDF of the call time? So what is the average call duration for all those calls which were at least 2 minutes or above? So if you understand now this the nature of the conditioning event, we can approach the solution. I'll again repeat. This is the unconditional distribution of the call time. So it includes all the calls from 0 onwards till any duration, and the average call duration for this case is 3 minutes. But now I put the conditioning event and I say for all those calls which are at least 2 minutes, what is the conditional distribution of the call time now? So I'll basically be excluding all those calls which are below 2 minutes. So our conditioning, I'll approach the solution. Our conditioning event is that t is greater than 2. So if this is the case, you know to find the conditional PDF, you have to divide the parent unconditional PDF with the probability of the conditioning event. So to find the probability of this particular conditioning event, which is probability that t is greater than 2, you will simply integrate from 2 onwards, 2 to infinity, the unconditional distribution, and this will easily reach at e raised to power minus 2 by 3. So if this is known, you can find the conditional PDF of the call duration time given that t is greater than 2. So this t greater than 2 is nothing but like b here, and its probability, the probability of b as denominator, has been found as such. So this basically by formula becomes f sub t of t, the unconditional distribution divided by the probability that t is greater than 2. And so this becomes 1 by 3 e raised to power minus t minus 2 all divided by 3 for t greater than 2 and it is equal to 0 otherwise. So hopefully you understand this concept. So now you know the conditional distribution of all such calls which are at least 2 minutes and onwards. So we have been able to find the conditional PDF. How to find the conditional expectation? Just as an extension, the conditional expected value is, conditional expected value means the average call duration for all those calls which are at least 2 minutes long. The conditional expectation here would mean the average call duration of all those calls which are at least 2 minutes. So you know this conditional expectation should obviously be greater than 2 minutes because even the smallest call is 2 minutes. So the average should be greater than 2 minutes. So how we can find it? By using this particular formula which says the conditional expectation is simply the parent random variable times the conditional PDF integrated. So now I simply write it as the expectation of t given that t is greater than 2 minutes. And so it is from 2 to infinity integration t time the conditional PDF. Remember this PDF, the conditional one, not the unconditional one. The unconditional distribution was this, but our conditional distribution is now this. So we'll utilize this in the expectation formula since it is a conditional expectation. So we'll use the conditional PDF, and so it is 1 by 3 e raised to power minus t minus 2 divided by 3 dt, and you integrate this and you will arrive at 5 minutes. So all those calls which are at least 2 minutes long, the average call duration is 5 minutes. So dear students, we have thoroughly discussed 3 topics in this particular lecture. Initially it was probability methods of derived random variables, then we learned how to transform continuous random variables, and ultimately we discussed the conditioning of a continuous random variables, and on the way we solved some interesting examples. Hopefully you have understood all those. Please do repeat this lecture and do solve and attempt all the homeworks given during the lecture, and Mr. Zevar Ali, who is the co-instructor in this particular course, will also give you assignment and further homework for your understanding, a deeper understanding of the topics. This also completes our chapter number 4, which is the single continuous random variable. In the next chapter, we'll start multiple continuous random variables. I'll deliver 2 lectures on multiple continuous random variables for week 14, and then I'll give 2 more lectures on the basics of stochastic processes, and then we'll end the course. Thank you very much for your time.